Okay, so we got almost the same relationship that we had for the buck boost. One difference is that now we have the N, the impact of N turns ratio, and the other thing is that the polarity are the same. So this is how we can find the relationship between output and input voltages in a flyback converter. So you use flyback. We use the volt-second balance. Now let's look at the current that goes through this capacitor. So again, dt and t. I'm sorry about the noise. My cats are playing and fighting with each other. So that's what's happening in the background. I'm so sorry about that. So when the primary switch is open, there's no current going through this diode. So this is gonna basically break the current loop. So we only have IC and IR going through this loop here. And you can see that IC and IR are gonna be equal, but with reverse polarity. So IC, it's gonna be negative VO over R when switch is on. When switch is on, when switch is off, what we have here, it's gonna be the DC component of the magnetic current. So the current that went through here, right? Let's call it IM. That's going to actually IO. And this is going to be IO over N, because it has to be converted back to this side, right? IO over N minus VO over R. Okay, so, and if we again I did it again, so this is, let's just make it. So let me tell you again, like, where this comes from. We have the current going through the inductor, right? And this basically gets stored in terms of energy in the magnetizing inductance of the isolated transformer. And if it gets converted, if it gets to the other side, it's going to be IO over N, right? Minus the current. So if this is the KCL at this point, minus the current that goes through the resistor, is going to be the I of the capacitor. So, and now we can write the, which rule? Amp second balance. So if you write the amp second balance, the volt second balance tells us that the average of voltage of the inductor is 0. What does amp second balance tells us? That average of current is 0. Current of the capacitor. So if we do this, then we can find the average of, so like I have to basically write VO over R times dt is equal to IO over N minus VO over R times 1 minus dt, and simplify this. And if you simplify this further, you just find that the average of IO, let's actually call it just I. This is like IO, like it should be on the other side. Let's just call it I. Average of I, which is the DC component, the average of magnetizing current, it's going to be equal to N times VO divided by 1 minus D times R. Okay, and we can also draw the input current it's gonna be, let's call it IN. The input current, it's just gonna be equal to I, which is the current that goes through the magnetic core, and then it's gonna be 0 for the rest of the time. So you know that average of IN, right? In this case, it's gonna be just D times I. Okay, so this is some of the analysis that we needed to do for the flyback converter. Now let's look at other waveforms. I have them somewhere here, so let me just bring them up and look at some other waveforms. So we looked at VL, we looked at IC, we looked at IN, and we derived the relationship between VO and VIN. And we found the current that goes through the magnetizing inductance. Now, I want to find the voltage across this switch. Why is this important? Because whenever you want to choose the switch, you have to know what's the maximum voltage that goes across the switch, right? So when the switch is on, the voltage is going to be 0. When the switch is off, right? This let me just call the, let me actually write the V1 is equal to VQ, which is V of the switch, plus V across the primary side. Okay, and this one comes from VO over N. This is the same as VO over N, right? Actually, it's going to be negative VO over N.